Alright, here we are again talking about color. Just kind of refresh a little bit. We were talking a little bit about the basic primary additive colors. And here we have three spotlights. We have one that is blue, shining from this direction across that way. We have a green light from here, and we have a red light shining from this direction. Now what's interesting here, in the front of the ball it basically appears white because all three colors of light are hitting there, so it appears to be white. Alright? But if we look right here, this side is being shaded from the red, and so you're really only getting the blue light and the green light, and so you get a cyan color. Now, the green light's coming right down the middle, so the shadow behind the green light does not have any green, and therefore it would have the other two colors, which are red and blue, and therefore you get a magenta or purplish color. And then on the right side over here, it's in the shadow of the blue light, and so you should be getting a yellow light here because the green and red light together make yellow. Okay, and we'll try to look at an example of this when we come up in the lab. But basically, where all three mix together, once again, it makes white. Therefore, they are considered complementary colors. All right, and so that is mixing light. Now, it's a little hard for us to get used to that. If you put red and green light together, you'll get yellow light. But think of it as being additive. We said these were additive colors. If you add more light, it's going to be a brighter color. Okay, if you add blue and red, you're going to get magenta. And if you add green and blue, you get light blue-green kind of, which is cyan. Okay, cyan. Now, that is different than if we try to mix pigments. Usually when we talk about mixing colors, say we're mixing paints. If we mix all the colors of paint, rather than getting white, which we do if we get all the colors of light, we get black. Okay, and that's because we're usually working with pigments, and unlike light, which is giving light, and so the more lights you have, the brighter the lights get until you finally get to a white if you have all of that together. Pigments subtract light. So for example, if you are looking at yellow, a filter that is yellow, it only allows yellow light, which would be basically red and green, and it's subtracting or absorbing out the blue light. If you have a magenta colored filter, it's letting the red and blue light through, and so it makes a magenta color, but it is blocking out or subtracting, if you will, the green light. Okay, if you have a cyan filter, then it is letting either blue or green light through as a cyan, but it is blocking out all the red, so it's subtracting one of the colors. And so these three colors are called the primary subtractive colors. Yellow, which is subtracting out the blue; magenta, which is subtracting out the green; and cyan, which is subtracting out the red. Okay, so if we take these filters, if this one subtracts out the blue, and therefore you get red and green, which makes it yellow. If you take this one, which blocks out the red, okay, and it only lets the blue and green come through, when you overlap them, the only color these two have in common that will let pass through is the green light. And so you've subtracted two colors, basically. When you overlap them, you're subtracting the blue and the red, and you'll have green left. On this hand, you have magenta, which has subtracted out the green, and you have yellow, which has subtract out the blue. The only thing left where they overlap, the only color they will let through is going to be the red. Over here, where you have cyan has gotten rid of the red, and magenta has gotten rid of the green, the only one that is allowed to go through here then would be blue. And so you've subtracted two colors out when you let these overlap and mix them. And if you let all three of them overlap, then they're going to subtract out all color, and you end up having black. Black is kind of like cold. We said cold is just the absence of heat. Okay, well, black is just the absence of light. If no light is reflected to your eye, then you see things as black. And so subtractive colors, the three primary ones, then like I said, are yellow, which subtracts out blue; magenta subtracts out green; cyan, which subtracts out red. But when you add them together, pigments and stuff like this, then they subtract out more colors. And that's why when you mix all the colors of paint together, you usually end up with some kind of black or a very dark color like that, because they're absorbing more and more of the different wavelengths of light, and so it gets darker and darker. Whereas when you add additive colors of light, then it gets brighter and brighter and becomes white when they're all mixed together. Now, if we see an object that looks yellow, then it is basically absorbing blue light and it's reflecting green and red, which to our eyes will be interpreted as yellow. If you see a object that's magenta colored, then it would be absorbing green, but it would be reflecting the other colors of light back to us, the red and the blue, and we see it as magenta. Okay, and the same thing with cyan here. So actually, when we see green plants, it's not because they're using green light, but rather they're reflecting it back. They are absorbing the other colors of light, and so those are what are actually useful to the plant. So that's kind of interesting there, because the colors we see are the ones that are not used or absorbed by the object. They are just reflected back to us. Now let's look at some other phenomena of color that we see in the world around us, and let's start with the age-old question that kids are supposed to ask their parents: why is the sky blue? All right, and we're going to be able to answer that now. In the atmosphere, most common gases are oxygen, or O2, and nitrogen molecules. Now, these absorb light, and then they re-emit it, or send it back out again, okay? And we call that scattered. We say it's been scattered. What it is, the atoms actually absorb the energy from light, and they re-emit it, okay? And it turned out that the higher the frequency of the light, the more likely it is to be scattered. And so if you look at light, the formula for that is Roy G. Biv formula, but actually the setup for that, Roy G. Biv is red, orange, yellow, green, blue, indigo, and violet. Now, as you go up this direction, they're getting higher and higher frequency, and it turns out that the higher frequency lights are more likely to be absorbed and then re-emitted. And so, and our eyes are not very sensitive to the violet end of here. We're getting close to ultraviolet light. We don't see that very good. So the first color, the highest frequency that we see very well, is blue. And so that's why we see a blue sky, because when those higher frequencies of blue light are absorbed by the atmosphere and then they're re-emitted and scattered in different directions, then we see those lights more often, that color. Now, if the air is very humid, all right, with a high humidity or a lot of water molecules in it, or if it has larger particles, possibly dust or pollution, then it will scatter other frequencies of light, okay? And therefore, since you get more colors, then they're going to be closer to white, and therefore the skies will be paler blue or almost whitish, okay? And that's usually a sign of some kind of pollution. A lot of times people talk about how blue the sky looks like after a rain. Well, part of the reason is it's washing those larger particles out of the air that are scattering other frequencies of light and make it more white. And if it's just the oxygen and the nitrogen, which is in the atmosphere all the time, then they tend to be a darker, richer blue color. All right? Now, if you get extremely large pollution particles, they tend to just absorb the light and not re-emit it at all. Okay, and that usually results in either a brownish haze, different colors depending probably a little bit on what kind of pollution particles there are, but the brownish, yellowy, orangish haze sometimes, especially if you look from a distance over Fort Worth, Dallas, or certainly if you're out in Los Angeles or any other big city where they have lots of pollution from cars and factories and so forth, then you're going to see that haze in the air, and that's from the larger particles. And rather than scattering, which is re-emitting the light, they're actually absorbing that light, and so it gives that darker, yuckier color. Also, we're talking about the sky. We should talk about clouds. Clouds we tend to think of as, ever since primary school, if you're going to do clouds, then clouds need to be colored white. Okay, but if you really look at clouds, you'll notice that most of them are not white. Some of them are part of them, even the fluffy cumulus clouds. Yeah, they're bright white here and there, but they also have darker colors in the blues and grays and yellows and even greens and other colors, okay? And so basically, a cloud is basically made of small water droplets, okay, and clusters of water droplets, kind of like fog, basically. And the tiniest clusters are going to reflect blue again. And so once again, if you have smaller ones, we'll see that. Okay, medium size will reflect green, which is kind of in the middle here, and the large clusters will reflect red. Okay, and so if you have clouds that have a combination of all these, they're going to combine together and give you basically a white cloud. And so in general, we say clouds tend to be white. But depending on if you have more of one size particles or the other, then they can have these different colors. Now, once again, just like the pollution, once these droplets get bigger and bigger, okay, and have more water molecules on them, they tend to absorb more light, okay, and rather than just reflect it, okay. And so as the rain clouds get darker and darker, basically that means the water droplets in the clouds are getting bigger and bigger, and they're getting ready to be big enough they can fall. And that's why when we see dark clouds in the distance, so ooh, there's rain clouds coming, because we know that you can see that. And actually you can see kind of like a veil coming down from those clouds a lot of times of just dark rain in the distance. Okay, it looks darker where it's coming out of it. You can just see the dark clouds, but it also looks dark where the rain is actually falling, because those rain droplets are absorbing the light rather than reflecting it. Last thing we're going to talk about, kind of, as once again, weather and skies and stuff like that. Why are sunsets usually red? Well, basically we said that blue are more likely, these higher frequencies are more likely to be absorbed and scattered, and that means the colors that are most likely to come all the way through then are going to be the long wavelengths, okay, and therefore low frequency lights, and the red, orange, yellow thing. Now, when the sun is overhead directly, there's a short path of air that has to get through, and so most of it does not get scattered, and so most of it comes through and we see a blue sky. Okay, but as we're turning away from the sun and it's having to go through more and more of the atmosphere, okay, more of the blue light's being scattered, and the light that actually comes to our eyes then are basically red, orange, and yellow. And so it gives it kind of that yellowish red, orangey sunsets that are always so pretty, and so forth. Now it can also be affected by the amount of dust and stuff in the air, which may make it even prettier. Dust may be hard to breathe in the air, but it definitely does make for prettier sunsets. Okay, and so, but since these are less likely to be scattered, as they have to go through more and more layers of atmosphere to get to us on the Earth, then we tend to see those reddish orange colors more around sunrise and sunset when it's having to pass through a bigger area of atmosphere. Whereas at noon, the sun's coming short straight through, a lot of this blue light and so forth does not get scattered, and so we see it. It comes to our eyes and we see the blue light when it gets there. Alright, and I think that's about wraps it up for light, and we'll see you in chapter 14.